Hello everybody. Okay, today we're going to be looking at an assignment on conservation of momentum. So we're going to be using the law of conservation of momentum mathematically. The law of conservation of momentum states that before and after an event takes place, the total momentum of the objects in the system must stay constant. When an event takes place for an isolated system of objects, as long as there are no outside forces, then momentum is conserved. Now, it will be transferred from one object to another or back, but the total before the event and after the event will be the same. So I like to say the sum of the momenta of the objects before the event, I use this for the event, must equal the sum of the momenta of the objects after the event. Okay? So all you have to do is determine first what information takes place before, what information takes place after the event. So let's look at this example problem that they've actually done. And then I'll show you how to solve it. I guess I better get my calculator, hadn't I? It would help, wouldn't it? Okay, here we go. All right, make sure it's on for when I need it here in a moment. Yeah, it's on. Okay. So, basically, look at what we have. And I'm going to use two different colors to distinguish. It sometimes helps, okay? All right. We've got a car A, and car A we'll call object 1, okay? So car A has a mass of 1,100 kilograms. So here we have mass 1, initial 1,100 kilograms. And it's moving right now at 20 meters per second. So the initial velocity of car A is 20. Then it says car A collides head-on with car B of mass 1,300 kilograms. So now we have another car. We're going to call that mass 2. And it has a mass of 1,300 kilograms. And right now, car B is moving at negative 15 meters per second. Now notice, what do you think the negative means if car A had a positive 20 meters per second? Well, it means they're going in opposite directions. One is going in the positive direction and one is going in the negative direction, and that's important. So we must have the negative on our value. So this is what they're doing before they collide. Okay, each one is moving with its own velocity. And in fact, here we go, right here. Before they collide, here's the event, collision. And before they collide, okay, mass 1 is 1,100 kilograms. Mass 2, and it has a velocity of 20. Mass 2 has a value of 1,300 kilograms. And its initial velocity before collision is negative 15. So these are the initial momenta. So we've got them in their places. The first thing I'm going to do is I'm going to find those two values. Okay? So we take our calculator. All right, and I'm going to say 1,100 times 20 equals, and that gives us 2,000. All right, so we have 2,000 kilogram meter per second, okay, because you've got kilogram times a meter divided by a second. Now, the next one, 1,300 times negative 15. All right, let's stick that in there. 1,300 times negative 15, okay, and we get negative 19,500. Make sure I put that in there right. Yes, I did. Okay, so we get negative 19,500 meters per second. kilogram meter per second. Sorry, kilogram meter per second. Oh, you know something? I made a boo-boo on that first part, didn't I? I just now noticed. It was 1100, and I did it again, didn't I? No, yep, I did. Clear. 1100, there we go, times 20, and that gives us 22,000, 22000. I'm sorry, guys. All right, so 22000. Now we're correct. All right, so here's what we have. This is the momentum before collision. So now let's get the total before collision. So we're going to say 22000 minus, when you add a negative, remember it's like subtracting. So minus 19,500. All right? And we get 2,500. So the total momentum before collision here is 2,500 kilogram meter per second. That's the total momentum of the system. All right? Now let's look at after. All right? We still have car A. After collision, watch this. Car A is moving at -6 meters per second. So here we go. 1,100 kilograms, -6 meters per second. In fact, they put it right here. After collision, 1,100, -6. Car B's velocity after collision. Ooh, we want to know that. Okay, so we've got the mass times the velocity, the final velocity of car B. So we've got the momentum of car A after collision and the momentum of car B after collision with our unknown. So let's look now at values, all right? So let's do this one first. We've got 1,100, oops, I don't think I did that right. Nope, did it again. It's 1100, and it's times -6. Okay, so that's going to give us a value when I hit enter of, there it is, can y'all see that? -6,600. Okay, so we're going to write that here, -6,600 kilogram meter per second. Plus, now here we can't multiply this out yet, so all I can say here is 1,300, okay, times the final velocity of mass 2. Oops, I wrote it backwards. Oh, well, that's okay. We'll flip it on the next one. All right, so VF of 2, car B. All right, so now down here we've got -6,600 kilogram meter per second plus 1,300 times V2F. There we go. Velocity of car 2 final, okay? Now, how do we get this? Here's how. It's a little tiny bit of algebra. Don't worry if you haven't had it. I'm going to show you right here. In order to isolate this, we need to first take this to the other side because this is a number, this is the number. No variables. The only variable we have is right there. So let's take all the non-variables to the other side. So we're going to add 6,600 to the other side because here we're subtracting it. So we're going to say 2,500 plus 6,600, and that would be kilogram meters per second, but I'll forego that for the moment. And that's going to leave behind 1,300 V2F. Okay? We're almost there. Now, we want to isolate the V2F. What is that value? Well, we're multiplying it by 1,300. To get the 1,300 to the other side so that your variable is isolated, you do the opposite of what it's doing. Right now, it's multiplying V2F. The opposite of multiplication is division. Just like up here, we were subtracting this. The opposite of that is adding, so we added it to the other side. Here, we're multiplying, so we divide to the other side, like this. That takes care of that, okay? So now all we have to do is stick it in our calculator and see what that is. So it says 25. Okay, 2,500 plus 6,600, enter, okay? And now I want to divide by the 1,300, enter, and our answer is 7. So car B, and notice it's a positive 7, so car B will be moving in the positive direction. It'll change direction. Notice at first it was moving in the negative direction, wasn't it? But when it collides with car A, it will change direction. It will go back the other way at 7 meters per second, almost half the speed, okay? But in the other direction. So there's our answer right there, okay? Now, if you go step by step, this is not hard. The idea is simple. The total momenta of the objects before the event, in this case a collision, must equal the total momentum of the objects added together after the event. Okay? Let's look at another one. This one's a little different. In this case, you have a shark that's going to swallow a smaller fish. So the event here is swallowing. All right? So we're going to have before swallowing and right after swallowing. Okay? Now, look what they tell us. We have a 10 kilogram shark. All right? So we're going to call that mass 1. So we're going to put 10 kilograms right there. Okay? It's swimming right now at 5 meters per second. So that's its initial velocity. So we're going to put, for V1 initial, we're going to put 5 meters per second right there. Now, it swallows an absent-minded half a kilogram fish. So here's our second object. Half a kilogram for mass 2. So put 0.5 kilograms right there. It says that fish is originally at rest. In other words, it's not swimming around, it's just sort of hovering over the bottom there, okay? So its initial velocity is 0, okay? Then they want to know what is the speed of the large fish after eating the smaller fish. Well, now here's the catch. Notice their masses are now together. So we can't have two separate objects. We have to say, 10 plus 0.5 kilograms. We have to put them together. They're one object now. And we want to know what is their final velocity. How fast will the big shark be swimming along with the little one inside? Okay? So let's take a look at what we do now. We're going to fill in the parentheses here. So we want the momentum of the shark first. Remember, the shark is mass 1. And we want before collision. So we've got 10 kilograms times 5 meters per second. Okay, also before swallowing, before the event, we've got the little fish. He has a mass of 0.5 kilograms and a velocity of 0. Of course, what is 0.5 times 0? It's going to be 0.5. So technically, for this entire system, the only momentum we have before the swallowing is just the sharks. But just for purposes of being technically correct, let's put 50 kilogram meter per second there. 5 times 10 is 50, you know that. Plus a big fat goose egg, 0. So now the total momentum before collision is just 50 kilogram meter per second, because you know 50 plus 0 is 50, okay? Now, let's look at the after side. Let's see what we've got. After collision, the two are together. So we have 10 plus 0.5, that would be 10.5 kilograms, wouldn't it? The little fish is inside the shark. And we want to know what is their final velocity. Okay, well, all we have now is just 10.5 times the final velocity. All right, now, how are we going to get VF? Well, we've got to isolate it. That means we've got to get rid of the 10.5. Right now, we're multiplying the 10.5 times VF. So over here on the other side, we're going to divide by it, okay? That gets rid of that, and we're left with VF on this side. Now the rest is easy. So what we're going to do is we're going to take our calculator, and I'm going to stick in 50. Whoops, wait a minute, I think it turned off. Whoop, there it goes. All right, 50 divided by 10.5, because the fish and the shark are together now. And we get 4.76, or if you want to round a little bit, 4.8. All right, 4.8 meters per second, because the kilograms are going to cancel here. All right, and that's going to be the final speed of the shark little fish combination. All right, so notice how we did that. Since they're together, we made them one object with the sum of both masses and however fast they're moving. Okay? So these are two good examples of how to use conservation of momentum. And if you just make sure that you very carefully look at what's going on before and what's going on after, make sure you use those subscripts, okay? Label one object, mass 1, one object, mass 2, all right? Just like they did here. And then you've got initials and you've got finals, and you just stick them in where they go. It's not so bad, is it? Now, if you will read the instructions on your, hang on, let me get to it. Boy, there's a lot of noise out there in the hall today. If you will read the instructions on today's assignment, you're not doing all of these. I think if you've scrolled through it, you'll see there are like 9 problems, including the one that we just did right here with the shark and the fish. But the only ones I really want you to do are number 2, 3, 4, 5, and 6. 2, 3, 4, 5, and 6. You do not have to do 7, 8, and 9. I think 5 of these is quite enough to be going on with, okay? So follow the pattern. They've got it set up for you in each problem. All you have to do is identify the information and put it where it needs to go here, and then transpose it over here into the formula. Guys, it's not very hard, okay? They've got it all set up for you, so that's nice, isn't it? You just need to know what the event is that you need to look before and after, all right? What is the event that's taking place? All right, if you have any further questions when you get started on this, please message me and I'll try to do my best to help you, okay? See you soon. Bye-bye.